Hello, and welcome to A Slice of Physics. In this video, we'll talk about conductors and insulators, and we'll also discuss how electrons move through a material. So from your experiments, you may know that charges can be transferred by touch from one object to another. So for example, suppose I have a block of wood like this, or plastic. So wood and plastic are called insulators, and we'll see why that is in a moment. But suppose then I bring up, so let's say this is plastic, and let's say then I bring another piece of plastic. This is also a piece of plastic, and let's say it has some extra negative charge on it at the end. If I were to touch the two pieces of plastic, then it's possible that some of the negative charge would rub off onto the other piece of plastic. So, and now my question is, where would that charge go? So let's say that two pieces of charge rubbed off onto this piece of plastic. So there are two pieces of charge sitting there. Will they stay there, or will they sort of move around inside the plastic? It turns out that in an insulator like wood or plastic, these charges will just stay wherever they're put. So that's what makes it an insulator, is the charges cannot move through it freely. So that's if this is plastic and this is plastic. On the other hand, suppose I have a piece of metal and I bring this piece of plastic up to it, and it has some negative charges, and let's say it manages to put them onto the metal. So now the charges are here. What will happen to them? So it turns out that in metal, those charges are free to go wherever they like. They can move around just as you can walk around a room. They can go straight through the center of the metal with no problem. So what they will do, what will they want to do? Well, they're negative charges, and they want to, of course, go away from each other because they repel each other, since they're both negative. So maybe one of them will go to one end of the metal, and the other will go to the other end of the metal. They'll get as far apart as they possibly can. Okay. So what we conclude is that in the wood or plastic, the charges stay where they're put, but in the metal, the charges repel each other to get as far away from each other as they can. So let's consider next what will happen if the plastic rod on the right brings in some positive charges. So here is, I'm bringing in some positive charges with the plastic rod on the right, and let's say these are both plastic. So now if I touch them, will the positive charges jump across and get into the other piece of plastic? No, that can't really happen because the positive charges are protons, so they're stuck to the other atoms. They're stuck to their atoms, and the atoms are stuck to other atoms. They can't leave. So what will happen instead is I'm going to have to draw the negative charges. So on the right, we have some other positive charges. Of course, there's all sorts of positive charges all over this object. And next to each positive charge, it has its own negative charge. Here's another positive charge. It has its own negative charge. Another positive charge. It has its own negative charge. But these extra positive charges have no negative charge. That's what makes them extra. So we don't draw the paired up positive and negative charges when we draw this diagram because they have net zero charge. They cancel each other out. The only thing that has a net charge is these extra positive charges that we draw. Now in this piece of plastic, which has no net charge, still there are atoms, and in each atom there are some positive charges and some negative charges. So if we were to draw a true picture of all the charges in this piece of plastic, we would have to draw like this. So when I touch them, is it possible for the positive charges to move? No, the positive charges do not move across from one plastic to the other, but the negative charges can. So it's possible for these negative charges to move across by touching. If that were to happen, then what would the situation look like? Well, it would look something like this. If the negative charges were to go across, then we would be left with these positive charges with no negative charges of their own sitting on this side. So it would look as though the positive charges had moved across, because remember, the positive charges used to be on the right, now they're on the left. So now the question is, what would happen to these two positive charges? Would they stay where they're put, or would they move freely throughout the plastic? Well, they would just, of course, they would stay where they're put, because the positive and negative charges in an insulator can't move around. Now, for one last question, let's consider what would happen if this object were metal. And I bring this plastic object over, and it has two positive charges. And I'm going to draw this whole thing again. So it has these atoms. This is a piece of plastic, so it has atoms in which there's a positive and negative charge. In the metal, the electrons are free to move, but they still have an equal number of electrons as protons. So now the same thing is going to happen. The negative charges, if with the touch, the negative charges could move across. So I moved them across. And now in the metal, what will happen? Will the protons move throughout the metal freely? No, the protons are stuck where they are. But remember, the electrons can move freely throughout the metal. So these electrons over on the left, they're all crowded together. And they say, we don't want to be crowded together. We want to move as far apart from each other as possible. So what's going to happen is some of these electrons are going to move around. Maybe this electron way over in the upper left-hand corner is going to say, I feel really crowded over here. I would like to move. So maybe that electron comes over here. And now the electrons are a little bit more spread out. And by spreading themselves out, of course, what have they done? They've made it so that the two positive charges are on opposite sides of the metal. So the positive charges do distribute themselves as far apart from each other as they can, but they don't do it by moving, they do it by the electrons moving. Still, when you're solving problems about this, it's sometimes easiest to think in terms of how the protons are moving rather than how the electrons are moving. And in terms of I wanted to say one more thing, which is that I've drawn in these pictures all of the charges moving from one piece of metal, one piece of plastic to another piece of plastic. So of course it may be that only some of the charges move over, but I wanted to draw two charges moving across so that you could see how the charges move around. But if there were more charges moving across, then there would be more charges that would all have to try to get as far apart from each other as possible. In the metal or in the plastic, in the case of the plastic, they wouldn't be able to move around. So in your book, there's an example where there's a metal sphere over here and another metal sphere, and there's a rod that connects them, which can either be plastic or it can be metal. And then we attach some charges to the metal sphere with this. Maybe this is a plastic rod that deposits these pieces, these electrons onto the metal sphere. And the question is, where do they go? Well, the book says if this rod is metal, then the electrons distribute themselves as far apart as they can. So some of the electrons go here, and some of the electrons go here, they try to get as far apart from each other as they can. On the other hand, if this rod is plastic, then the electrons are unable to move across the rod, and then they get all stuck in the metal sphere on the right. So that's the difference between conductors and insulators, and how electrons move throughout metals. Thank you.